Wastewater treatment plants consume energy, but it is possible to recover part of the energy that wastewater contains and exploit it for several uses. Energy in wastewater is present in different forms. As thermal energy, the heat energy of wastewaters recoverable through heat extraction; as hydrodynamic energy, the kinetic potential energy of influent wastewaters; and finally, as chemical energy. Let's focus today on chemical energy. What do we mean with chemical energy? Besides ammonia, organic matter is the main source of chemical energy in wastewater. Two analytical determinations are commonly used to measure the organic matter of waste: the chemical oxygen demand, COD, and the volatile solids, VS. The COD describes the amount of oxygen needed to chemically oxidize all the organics. The VS is a gravimetric measurement that allows estimating the amount of organic material in a dried sample. But how can we recover the chemical energy contained in wastewaters? How can we produce biofuels from a waste? The conversion of wastewater streams into bioenergy has a long history, especially through anaerobic digestion producing biogas. Several technologies are under current development to convert organic matter to diverse biofuels, such as biodiesel, bioethanol, or char. The most common solution in conventional wastewater treatment plants is still biogas production from anaerobic digestion, as the other options are still at an early stage of their technological development. Let's find out how the anaerobic digestion process is integrated in wastewater treatment plants. The organic matter is removed from wastewater by different physical and biological processes, and the fraction that is not physically separated or oxidized to carbon dioxide ends up in primary and biological excess sludge that must be stabilized before disposal. Here comes into play anaerobic digestion. By exploiting the anaerobic metabolism of specific microorganisms, the biodegradable fraction of sludge is converted into biogas, a fuel gas mainly composed of methane and carbon dioxide, which can be burned in combined heat and power units for heat and electricity generation. All treatment units at conventional wastewater treatment plants are energy intensive, except anaerobic digestion. Anaerobic digestion proceeds through a series of parallel and sequential interdependent reactions that have been typically grouped into 4 steps and that are carried out by a complex and diverse microbial community. Hydrolysis, where complex substrates that cannot be directly utilized by the anaerobic microorganisms are broken down into simpler molecules. Acidogenesis and acetogenesis, also known as primary and secondary fermentations respectively, where hydrolysis products are converted into intermediate compounds. Methanogenesis, during which methane and carbon dioxide are produced from acetate, hydrogen, and carbon dioxide, generated during the 2 previous fermentation processes. Several physical and chemical parameters affect anaerobic digestion processes, and temperature is one of them. Indeed, temperature has a strong impact on the kinetics of all processes occurring during anaerobic digestion. Mesophilic processes operate in a temperature range of 30 to 40 degrees Celsius. Mesophilic conditions are the most commonly applied process conditions, being normally a favorable compromise between digester heating requirements and process kinetics. Indeed, mesophilic conditions support the largest range of microorganisms, and this diversity allows for process robustness. Stoichiometrically and theoretically, from each kilogram of COD biodegraded in the process, about 320 to 330 liters of methane can be generated. Depending on the concentration of organic matter, in the wastewater, 5.5 to 7 megajoule is the chemical energy content of 1 cubic meter of municipal wastewater. However, only 10 to 14% of the initial theoretical value can be recovered for 2 main reasons. Part of the COD in the wastewater is not biodegradable, and part is removed through aerobic processes. In addition, the anaerobic degradation of biodegradable fraction of sludge is usually limited to 70 to 80% for technical reasons, such as the non-ideal reaction conditions in digesters. So why not recover most of the energy potential in the wastewater itself, rather than the fraction currently recovered from sludge? Let's find it out. Actually, in the biological processes applied to treat wastewater, the energy potential of most of the degradable organic matter is not recovered but converted into carbon dioxide by energy-intensive aerobic processes. By contrast, common anaerobic digesters are to treat highly concentrated streams, such as waste sludge. These anaerobic biological reactors are compact and simple, and their volume is defined by the loading rate to be treated and by the reaction time required by the process, commonly 20 to 30 days depending on the type of substrate. Hence, large volumes increase biogas recovery by completion of anaerobic process kinetics. However, higher volumes also imply increased mixing and heating expenses. Actually, the waste sludge rate separated with primary and secondary clarifiers is averagely 2 orders of magnitude lower than the influent wastewater rate. Accordingly, treating wastewater through conventional completely mixed suspended growth anaerobic digesters would require huge volumes and huge energy consumption for heating. However, the successful and quick development of anaerobic membrane bioreactors ANMBRs may further expand the application of anaerobic digesters to a range of new substrates, including wastewaters. Its main advantage is the total retention of particles through membranes, then producing, besides biogas, high-quality effluents free of solids and pathogens. Even so, several issues limit their commercial application, mainly the limited energy recovery, which largely depends on the concentration of biodegradable COD, the membrane flux, the energy spent on fouling control, and process temperature. At present, the implementation of ANMBRs as a mainline process for municipal wastewater treatment plants is still under development, and it is expected to increase in the near future. Let's focus now on biogas, the most interesting anaerobic digestion product in terms of energy. The presence of carbon dioxide reduces the energetic density of biogas, making it usable only on-site in a low-efficiency way. In view of this, biogas upgrading is becoming increasingly important today. Indeed, carbon dioxide can be removed using physical or chemical processes, or even converted into methane by exploiting, once again, specific anaerobic microorganisms able to produce methane starting from carbon dioxide and hydrogen. The resulting biomethane, containing primarily methane at 97 to 98%, can be injected into the existing natural gas grid. Hydrogen can be supplied from water electrolysis using renewable electric power to split water into hydrogen and oxygen. In the case of a power-to-hydrogen system, hydrogen is the final energy carrier. In contrast, power-to-methane systems further convert hydrogen into methane in a second biological step by introducing it together with carbon dioxide from biogas. Besides biogas, hydrogen can also be produced through biological processes. Dark fermentation is part of the full anaerobic digestion process. Microorganisms degrade carbohydrate-rich substrates into simpler organic compounds with simultaneous production of gaseous hydrogen. However, its commercial feasibility is limited by several factors, including low hydrogen yield, process instability, and the need for reducing the presence of hydrogen-consuming microorganisms. Furthermore, poorly biodegradable substrates, such as waste sludge, need to be pretreated to reach acceptable hydrogen yields. In the medium term, dark fermentation will not displace anaerobic digestion as the main technology to convert organic-rich waste and wastewater streams into bioenergy. However, the capability of dark fermentation to produce effluent rich in volatile fatty acids makes it very attractive to be combined with other processes for energy and chemical production and to further stabilize the effluent. Compared to other alternatives, the combination of dark fermentation and anaerobic digestion may be a future possible option to upgrade existing anaerobic digesters that would be able to produce a hydrogen-rich biogas. This would improve the thermal efficiency and reduce the pollutant emissions due to biogas combustion.